Hello and welcome everyone. So we have added some additional capabilities to Swarm, which will allow distributed applications to store private or restricted access data on Swarm. And if some of you will have a slight deja vu with this talk, the reason for this is I have already talked about what we were going to implement or what we're in the process of implementing, but this time I'm talking about what we have implemented, and there are minor but very important differences. So first I'm going to talk about principles of decentralized access control, because in decentralized trustless and permissionless systems, the challenges of access control are slightly different. Namely, since we have no control over who has copies of the data and where and how it is transmitted, the centralized solutions where some trusted gatekeepers decide after checking the identity of the user whether they can have read or write access to data simply don't work, because you cannot count on nodes, which again, since the network is trustless and permissionless, you cannot count on them to actually keep out the parties that you want to keep out. And therefore, we apply a certain kind of transformation, and read access becomes the ability to decrypt. So anybody can download parts of your data, but only those to whom you have granted read access are the ones that are going to be able to actually make sense of it. And similarly, write access is transformed instead of a permission to override the data. Everybody can post new data into Swarm, but the ability to update the reference to that content that you have uploaded. Now, I'm not going to talk too much about write access. Actually, I'm not going to talk at all about that, because that's fairly straightforward. The same algorithms that you implement in a centralized system, you simply put them into your decentralized application, be it the update of some mutable resources on Swarm, or even update the references on the blockchain like in a ENS resolver. And the other transformation is that whenever you have some sort of identity, we're going to talk about public-private key pairs. Now, that's not actually everything we can do. So in the actual implementation of encrypted Swarm, we allow identities that do not have private and public key pairs, but only have usernames and passphrases. So that also works. But for the lack of time, I'm not going to talk too much about them, because they're the less interesting ones. Very importantly, in a decentralized system, basically the street from secret to a public is a strictly one-way traffic street. And this is true both globally and locally. So if you make something public, you can not put it back into Pandora's box, but also regarding a single entity, regarding a particular party, if you disclose something to a party, you cannot undisclose it. Which means that revoking access is not exactly like it's not exactly a complete reversal of granting access. Revoking access and granting access are not precisely the inverse operations of each other. They are slightly different. So whenever you revoke access, whatever those parties had access in the past, they will still have read access to. You cannot force them to forget the keys that they have been exposed to earlier, But it does mean that if there are future updates to some kind of private content, the parties that have been excluded, they are no longer able to access anything new, but they will still have access to old data or old versions of data. But of course, that data will be eventually garbage collected, but they might have saved it for themselves. So you cannot count on them not having access to it. In case of granting access, it may or may not include the ability to read the past history. So that depends on what exactly is in the new data and whether the new versions have references to the past versions. So that is up to the designer of the distributed applications whether they include that. But definitely, once you grant read access, it immediately implies the ability to share. So whereas in a centralized system, you can sort of distinguish between the two, that somebody can access something, but they cannot share. Of course, that never works quite well, because you can still copy the data and then share it. But in decentralized and permissionless systems like Swarm, the two things are one and the same. You cannot separate these two. So these are the basic principles. And now, before I actually tell you how it is implemented, I think that a brief introduction to how Swarm actually works is in order. Many of you might already know this, but I think that it's beneficial to do a quick recap. So first of all, Swarm is a layered system, just like the internet. And the bottom layer, the one in which most of the interesting stuff happens, deals with fixed size chunks which are passed around between nodes. Distributed applications do not have direct access. There's no API to this. There's no external API for this layer, but it is on this layer that the network level stuff happens, which means that in order to be a Swarm node, in order to participate in the Swarm network, this is the only layer that you need to be aware of. Everything else above it is basically application layer stuff. Then we have a layer which is the layer on which data structures and databases work. So let me refer back to the first talk of today by Elad. If you're implementing some kind of data structure on top of Swarm, then this is the layer on which you're operating, where you have arbitrary length data, and it is referenced by a, well, Elad called it a hash jest. We are calling them references because we also want to feel special, but it's the same thing. And above that layer, one of the things that Swarm provides is a virtual web server. So this is in order for web application designers to be, and developers to be able to write in a familiar environment, and also to be able to bring all the tools from Web 2 over to Web 3 with as little changes as possible. And of course, on top of that, we have the Swarm-hosted dapps. So that's the basic architecture of Swarm. What's a chunk? So a chunk is a, at most 4 kilobyte chunk of data with one piece of metadata added to it, which is 64 bits, which is the length of the underlying data. So if it's called the span. And if the span is more than 4 kilobytes, then it simply means that this chunk is an intermediate chunk, and its content is references to other chunks. So here's an example. Suppose you want to store 10 kilobytes, which is more than 4. In Swarm, this is how you store it. You need 4 chunks to do so. One intermediate chunk, the one on top, which also happens to be the root chunk. And it has 3 references to 3 additional chunks. The first 2 chunks are full, they're payloads, but that's just 8 kilobytes, so there's an additional chunk which holds the last 2 kilobytes. And these 4 chunks together constitute the 10 kilobytes, which are referenced by the single reference to this root chunk, this one. So this is the content-addressed structure of swarm. And so this is, just let me go back. So this is this layer. And on this layer, we implement a thing called the manifests, which are simple Merkleized key-value databases where the key is the path, so that's the URI of the content, and the value is metadata, so it's, as a bare minimum, it's the content type that is required, but you can also add additional HTTP metadata to it. And the other thing is a reference to the content. And in case of access-controlled content, here you have a reference that is encrypted. In the plain unencrypted swarm, this is just the hash of the root chunk. So next I'm going to talk about how content is actually encrypted in swarm. Very importantly, everything I will be talking about happens on the layer of chunks, so that's the bottom layer, which means that essentially swarm encryption injects a new layer here. So that's why you have this little curvy in that thing. So the encrypted and the unencrypted swarm differ only on this link, which means that participants in the swarm network nodes, they do not need to be aware of encryption or unencryption. So all they see is chunks, and the encrypted chunks look exactly like unencrypted ones. And also the applications above this do not need to bother a lot with encryption, because all they will see that the references are different. So for symmetric encryption, Swarm uses CTR mode. So this is currently the most common way of symmetric encryption, because it's the easiest to reason about and prove various security properties. This is a picture from Wikipedia, so you will find it right there. But what's important to notice here, that even though it has a block cipher, it actually only uses the one-way property of block cipher. So a block cipher is essentially a one-way function with a reverse gear. But in case of CTR, we never actually switch it into reverse, which means that any hash function would do just as well. You don't actually need a block cipher in that place. So here's the version that we use in Swarm. So this is just one of these boxes. So this is how we do it in Swarm. So instead of the block cipher, we use two SHA-3 hashes. One of them is a compression function, which means that it takes more data on the input than it outputs. And the second one is a simple one-way function, which is a substitution box, an S function. So why do we use a hash twice? Basically, two hashes in serial connection is just one hash function. They have the same properties as a single hash function, except that they're twice as slow. And the reason is the little red arrow there, because it gives you access to this point, and that allows you to do partial disclosure. So if we want to take everything that Elad explained about turning data structures into Swarm data, then we can also very generically take any unencrypted Swarm data and turn it into encrypted Swarm data, except that our references from now on are not just hashes, but hashes of the ciphertext plus the decryption key. So these two things together constitute the reference, and it has the same property that if you see the same reference, then you can be certain that it points to exactly the same content. The converse is not true, but it's not required either. And here, you can disclose the data which travels on that little red arrow, and thereby prove the plain text given the ciphertext without actually revealing the key. So this allows you for partial disclosure. Now, it suffers from one vulnerability, which in cryptography we call existential forgery, meaning that I can disclose some random key, like I am an attacker, I have no idea what the actual content is, but I take a random key, I put it here, I XOR the output with the ciphertext, and I get to some plain text. Not the original one, but some completely different plain text, which also looks like it might have been the content. So this is existential forgery. But I cannot satisfy any constraint on that plain text, meaning that if that plain text is in any way integrity protected within the data structure, then I lose the ability, as somebody with no actual knowledge of the content, I lose the ability to forge. So this is just existential forgery, not total forgery. So for most applications, this is perfectly adequate, and if you're careful about it, you can still use it. So let's summarize. So we have done a transformation which allows us to use all the machinery that we know from data structure research, and we applied it to unencrypted swarm. Now we can use the exact same machinery to keep and manipulate private data, which are only accessible to a certain group of users, but not everybody. The only difference is that the references got longer, so now they consist of the ciphertext hash and the decryption key. The API is not changed. So the encrypted swarm API exactly the same as the unencrypted swarm API, it's just that the references got longer. And I think at this point it's important to emphasize that it's not only the API, but also the data model. So you can take any data model you have, whatever comes out of Swiss, you take here, except you change the references from hashes to these ciphertext plus decryption, this ciphertext hash plus decryption key pairs. And those are your hash justs into the private data structures. So it's not only the API, but it's also the data model that hasn't changed substantially. And the only cryptographic assumption that we have here is the assumption of SHA-3 being a collision-resistant hash function. If this security assumption fails, we're having much bigger problems than Swarm not working. So that would kind of ruin Ethereum as such. And the important thing is that by using counter mode SHA-3, we have not extended the attack surface. There's no additional assumption in encrypted swarm beyond the security of SHA-3. And of course, because of this, it is smart contract friendly, because in EVM you have access to SHA-3, so you can do all these proofs within EVM. I will let you do the questions during the Q&A, okay? And the last part, I will talk about access management and asymmetric encryption. So identity is just like in Ethereum, a elliptic curve public key. Now, it's not, so this is a little bit of a hand waving, so it's not just like in Ethereum, because in Ethereum, it's really enough for the identity to be an Ethereum address. Unfortunately, in Swarm, that's not enough. You actually need the public key. So you do need the point on the elliptic curve, denoted here by Y, capital Y, which is the private key, X, times the generator element. So it's a little bit more than the Ethereum address, which is the hash of this thing. The plain text is the symmetric key, the one that we're going to use in the symmetric encryption as introduced before. And the ciphertext is basically the El-Gamal encryption, where plus is the XOR operation. And here you see the formulas for encryption and decryption. And we also have this new data structure called the ACT, or ACT, which is basically a trie holding a key value database of parties that are allowed to access the content. And the nice thing about it is, so again, here in the slide you see what's in there. So what are the keys and the values? But the interesting thing about it, the security property that I think is most valuable about it, is that even those who are granted access inside this act, they have no idea and they have no means of knowing who else has access to that same data. The only thing that this data structure leaks is an upper bound on the number of grantees. But that's just an upper bound. So even the actual number of grantees is not disclosed by this data structure. Again, to summarize, we use hybrid encryption. So the reference is encrypted using a symmetric key, and that symmetric key is encrypted multiple times in the access control trie. Modifying the access control list is just a modification operation on a trie, which means that a fairly small number of hashes and ciphers need to be recalculated, so you don't need to re-encrypt content whenever you're changing the access control list. And again, the read access and the write access are defined as below. So that is basically how we have transformed the unencrypted swarm into a very similar structure, which now allows for keeping confidential data. And so I'm taking questions now, so you were the first ones.
Okay, so this is rather far out, but I'm just curious. So far for the Ethereum 2.0 spec, they're leaning towards using Blake 2B as a hashing algorithm for the blockchain. Does Swarm intend on switching to Blake 2B, or do they not know since it's very far out so far?
So because Swarm only needs, can I have the mic? So since Swarm as a network doesn't need to know about encryption, it can be switched later. So all what I have said would work with any other encryption algorithm as well, as long as you can operate it in counter mode.
So you mentioned that basically also unencrypted data can be kind of self-encrypted with a derived key. I think that is a concept in Swarm. What implication does that have for potential deduplication of data? So if we have widely replicated data that should be uploaded again, does this sort of default behavior prevent content from being deduplicated because it has to be encrypted with a different key?
So thank you for the question. So deduplication in a privacy setting, it has a security property that if different parties encrypt the same data and they see that it's somehow the same, then it discloses something that the party would not have wanted to disclose. So in general, for different parties, there's no deduplication in encrypted Swarm. So if two different parties upload the same content, they will have no idea that they have uploaded the same content. However, if the same party is uploading the same content, the keys that are generated for each chunk there's no constraint on them. The only thing that is required that they are unique, that you do not reuse the same key for different content. However, as a client, and this is not yet implemented, but it's on the very top of our priority list. It will be implemented, I believe, in the next 1 or 2 weeks. The one way to generate those keys is to have a semi-permanent private key, or secret key more precisely, a secret key on your node, and you calculate the encryption key as the MAC of the content with that key. And that way you will have a unique key, and for the same content you will deterministically come up with the same encryption key, but since you never disclose that secret key with which you have actually calculated it, for any other party, any third party or second party, those keys are just as good as random. But you will have the deduplication provided by the fact that the same chunk will always get the same encryption key. So you can have deduplication for the same party, you cannot have deduplication for different parties. That's it. Hope I answered your question.
Anyone else?
Just a quick one. You mentioned that the only security property that you assume is SHA, but in fact, if you look at the bit bigger picture of usability, like, is there no problem with potentially leaking the decryption keys through remote access, for example, or some other way which users are kind of might fall into the trap of doing, and so that kind of changes the security properties.
So yes, so that you're right. So the assumption of the security of SHA-3 is the only cryptographic security assumption. There are also operational security assumptions, which I have not mentioned. And basically, if you're accessing Swarm through a gateway, that means that gateway would also need to access all your private information. Well, not necessarily all, but at least the symmetric keys. The symmetric keys need to be, the gateway, in order to provide you with a HTTP interface, would need to have access to the symmetric keys involved, which is a security risk because, you know, the gateway is not you, it's a other party. And if you don't want to trust gateways, and I really think you shouldn't, then in order to manipulate or even access encrypted data, you should really run your Swarm node, and there will be possibilities to have light nodes. So I believe that Swarm-enabled browsers, like the Mist browser published by Ethereum Foundation, are the secure way of accessing encrypted Swarm.
All right, so thank you very much, Donny.